Alright, in this video we're going to continue our discussion of benzene and other aromatic compounds and talk about why benzene is so specially stable. So the reason we spend basically 2 chapters on aromaticity is because aromatic rings are remarkably stable. We know that alkenes readily undergo addition reactions, where we can add various things, bromides, HX, waters, to the double bond. Aromatic rings are stable enough that they don't undergo such reactions. Benzene will not add bromine. The book goes through a more lengthy demonstration of the stability of benzene using heats of hydration. I'm going to skip that, but if you're interested, you can always go and look at that section of the textbook. So as we've done a lot these last 2 chapters, we can use molecular orbital theory to help explain the stability of benzene. So we have 6 atomic p orbitals. Those need to be conserved, so out of those we can make 6 molecular orbitals. And the shapes of the orbitals and their energies are given in this diagram. These are not easy to determine. They involve complicated mathematical formulas. Generally, you need powerful computers to solve these, but we're given the results here. And so benzene has 6 p electrons, or 6 pi electrons in the molecule that we can fit into these molecular orbitals. And so when we fill those up, we'll put 2 in the lowest molecular orbital, and then the next 2 molecular orbitals are degenerate, and so we'll go 1, 2, 3, 4, 5, 6. And so all of the molecular orbitals in the pi system of benzene are in bonding molecular orbitals, and this is what accounts for the great stability of benzene, right? And it also helps, right, this lowest molecular orbital is delocalized among all the atoms in the ring, and so the fact that all the electrons are in bonding molecular orbitals and this delocalization is what accounts for the great stability in benzene. And we really talked about this on the last slide. I've blown up the picture here, but again, it's the delocalization of the electrons and the fact that they're all paired and all in bonding electrons that are delocalized is what accounts for the special stability of benzene. Now, to think more about why benzene is so stable, let's compare it to some other compounds that it turns out aren't as stable. So here we have cyclobutadiene and cyclooctatetraene. Both of these look a lot like benzene. We have alternating double bonds, and we have these ring structures. It turns out these compounds do not show the special stability we would expect for an aromatic compound. And in fact, when we react cyclooctatetraene with bromine, it readily adds the bromine to it, right? This is in contrast to benzene that is so stable that it doesn't like to undergo these addition reactions. So let's use molecular orbital theory again to try and explain why these compounds are not stable in contrast to benzene. So we'll get to molecular orbital theory in a second, but it turns out what needs to happen for a compound to be aromatic is we have to have the ring with alternating pi bonds, or we'll see they don't necessarily have to be alternating pi bonds, but they have to be overlapping p orbitals. And then they also have to meet Hückel's rule. And so it turns out, in order to be aromatic, we need to have an odd number of electron pairs. Or the formula, it turns out, we need to have 4n plus 2, not pairs, but total pi electrons, where n is just an integer. So, right, if n is 0, if we had 2 pi electrons, and we meet the first criteria, a ring with overlapping p orbitals, it could be aromatic. If we have n is 1, so 4 plus 2 is 6, is in the case of benzene, right? That could be aromatic. Or if n is 2, if we have 4 plus 2 is 8, plus 2 is 10, that could be aromatic. So these are sometimes called Hückel's numbers. But if we have 4 electrons, right, that doesn't meet the criteria, right? 4 minus 2 gives us 2. That's not divided by 4. That's not aromatic. If we had 8 pi electrons, as we do in cyclooctatetraene, right, 8 minus 2 gives me 6. 6 is not divisible by 4, so 8 is not a Hückel number. So, at least based on this rule, we can see why cyclooctatetraene would not be aromatic. But now let's look at the molecular orbitals to see if they can back up this empirically determined Hückel's rule. So if we consider the molecular orbitals for cyclobutadiene, and again, these often involve complex calculations, so they're just given the energies here, we have a bonding molecular orbital. The molecular orbitals are sort of more symmetric in this case of cyclobutadiene, and so we have one bonding molecular orbital, we have one anti-bonding molecular orbital, and then these two fall at exactly the same energy, more or less, as the atomic p orbitals that we made them from. And so when we have this situation where we have, two orbitals or however many orbitals exactly in between the bonding and anti-bonding energies and exactly at the energy of the atomic orbitals, because they're not contributing towards bonding or contributing towards anti-bonding, we often call these non-bonding molecular orbitals. And so there are a couple things that leads to this instability of cyclobutadiene. So one thing, when we have unpaired electrons, that tends to make molecules very reactive. And so these two unpaired electrons is very reactive, right? And then also the fact that we have electrons in non-bonding molecular orbitals as opposed to all of them being in bonding molecular orbitals like they were in benzene. This is what contributes to cyclobutadiene not being aromatic. And in fact, when we have these overlapping p orbitals and it's not aromatic, we often see the situation where it's incredibly unstable, right? It's unusually unstable, more unstable than we would expect. And so this is actually called anti-aromatic. So we've mentioned a couple times over the last couple chapters that molecular orbital calculations can often be very difficult. They can be expensive computer-wise, they involve complex mathematics, and it can often take a lot of computer time in order to determine the energies and the shapes of these orbitals. One nice thing, though, is that there are a number of qualitative models that will allow us to make predictions about the relative energies of the orbitals. And one such method that was developed for ring systems like we've been talking about is called Frost circles. And so it provides a simple qualitative procedure for at least determining the energies of the orbitals in rings of overlapping p orbitals. And I've got the steps down here, but I have them blown up larger so they're easier to read, and we'll go through them more slowly on the next two slides. So in the official procedure, the first thing we do is draw a circle. I'll be honest, I often skip that step. Right? The key then is we want to draw the shape of our cyclic system. Right? In this case, we have cycloheptane. And we want to fit our cycloheptane in the circle. And then one of the keys is whenever we want to draw one of these frost circles, we need to have one of the points pointing directly down. Then at each one of the carbon atoms in our ring, that's where we're going to draw a line to represent the energies of the molecular orbitals. Then what we want to do is draw a dotted line through the center of the circle. And then erase the circle and the polygon. And I don't often erase the polygon, and I didn't draw the circle to begin with. Sometimes it can be tricky to draw the line and to know exactly where it should be in the center. When it's symmetric, it's easier. We want half of the dashed lines above of the molecular orbital energies above the dashed line, half of them below. In the case of heptane, right, we can't do that. But if it's not symmetric, the line shouldn't be going through any of the orbitals, and then we want it to be as close to half as possible. So this wasn't exactly symmetric. To be exactly symmetric, we would have had one at the top. And so the dashed line is not going to go directly through any of our lines. And so this is the point where it makes the most sense, even if it's harder to see. Right? If I put it up here, I'd have 2 above and 5 below. Right here, I have 4 above and 3 below. So this is sort of the best estimate for the halfway point. Anything above that line is considered an antibonding molecular orbital. If it happened to be right on the line, that would be a bonding molecular or a non-bonding molecular orbital. And then anything below the line is a bonding molecular orbital. And then all you have to do is figure out how many atomic p electrons or molecular pi electrons you have, and then fill up your atomic orbitals. Fill up your molecular orbitals. All right, so we've already seen why cyclobutadiene was not aromatic. Let's try and do the same thing for cyclooctatetraene. So we have cyclooctatetraene here. To help us out a little bit, I've turned my octagon so that I've got 1 point down as I would need for the frost circles. And then when I try to figure out where my middle point is, right, I have 1 and 2 and 1 and 2, and then these two are going to be right in the middle. So my dashed line is going to cut right through these two atoms. And so when I draw in the molecular orbitals where these carbon atoms are, right, those are going to be non-bonding orbitals. So for my cyclooctatetraene, my orbital energies are going to look something like this. And you could put them, you know, like I would probably put these guys in the center. You could line these three up and these three up, but I tend to kind of still draw it like an octagon, right? And then I'll use a different color. Let's put in a dashed line, right, that separates. So these two molecular orbitals are going to be non-bonding. These three molecular orbitals are going to be anti-bonding, and these three molecular orbitals are going to be bonding. And then the number of pi electrons I have in cyclooctatetraene, I have 2, 4, 6, 8. And so when I put in my electrons, I'll go 1, 2, 3, 4, 5, 6, 7, 8. And so we can see a similar picture to what we had in cyclobutadiene. Not all of my electrons end up in bonding molecular orbitals, so I wouldn't expect the extra stability of being aromatic. And then not only that, I have these unpaired electrons. So again, cyclooctatetraene, we would expect to be anti-aromatic. And so not only is it not more stable than we might predict, but it's going to be even less stable than we might have normally predicted for such a molecule. Now, this anti-aromaticity only holds if the molecule maintains its planar structure. If it bends, then it breaks up the conjugation, and now the relative energies of the molecular orbitals are going to be different than we saw when we drew the frost circles. So this is in fact what cyclooctatetraene does, right? It doesn't want to be anti-aromatic, right? Anti-aromatic is bad for stability. So it forms this tub-type shape to break up the aromaticity, and so then this breaks up the anti-aromaticity. So it's still not aromatic, certainly, but it can avoid being anti-aromatic by changing its shape. And then this is, I think, just a good reference slide. We've got the frost circles drawn for a number of sort of reasonably sized ring systems. And then you can see benzene here, the six-membered ring, right? This matches the relative energies that we got from the accurate calculations on the benzene molecule. All right, so in the next video, we'll look at aromaticity in compounds other than benzene.